to use that system on a train, just to show you that it is possible with adaptations to the system to mount this system on a train and do some sort of rail scanning. So it's a very flexible system, obviously aimed at generating a lot of points, maybe for tunnel measurement and things like that. You can see some examples up on the screen there. So moving on slightly then, how does the system actually capture data? I kind of covered some of these points, but let's look at that in a bit more detail. So we have two FARO focus laser scanners. You can see they're mounted there at an angle, a crisscrossing angle effectively. And what we would first of all do is do an initial calibration with targets on those two positions in order to give us effectively a registration between the two units. So we know exactly the position of the two mirror positions which are rotating, or the center point of each one. Okay. What actually happens then is we get this crisscross data effect. You can see as we're moving along the road, we're capturing a lot of information on one side, but also in a corresponding direction. And what that does is it minimizes shadow from other vehicles and things that are going through the path, and also results in a kind of checkerboard type pattern on the data. And to give you an idea of how that checkerboard would look, so two scanners running at about 96 Hertz. If we're traveling at about 36 kilometers an hour, that would equate to a scan line of about 10 centimeter spacing. So that is quite a dense point cloud to generate at that speed. Okay, and we have obviously a lot more data because we have these two angles of the two scanners. And if we did increase the quality of those scan settings, that would only increase the scan points per line. So we're effectively using the FARO focus at its maximum speed of about 1 million points a second. So if we just had one unit, as I mentioned before, if we just had one unit attached to the system, you see you get this helical profile mode where you have a kind of a circular gap between each of the scan lines. But by using the two scanners crisscrossing, you hopefully can see on these images a kind of grid-shaped pattern or a more dense pattern to the data. Okay, so it gives us a lot more detail on the environments around us. And with the Ladybug camera then, we have that sort of intensity data. On the previous slide there, if you look to the right, we have the intensity returns from the laser scanner unit. But on the left-hand side, obviously, you can see we've got colorized data. And to achieve that, we're using this Ladybug camera, which has about a 90% coverage of the full sphere, running at 10 frames a second. And we can space the interval of each of these images at about 3 to 5 meters. And so how does the system actually compensate for the movement of the vehicle? Okay, using an IMU on the onboard computer. Okay, here's an inside of the actual system, and we have some removable hard drives in there as well, so we can store data up to around about a week's worth of constant capture, sort of standard working hours. We can actually capture that data and record that and store that on removable hard drives. Using an odometer as well, we have velocity calculators. So if we have an odometer attached to the vehicle's wheel, we can actually calculate the speed at which we're traveling. So all of those different things then come together. So using the IMU and a combination of the IMU and the GNSS, we can calculate pitch, roll, heading very accurately. We then also can calculate the position that we are actually located in the real world using the GNSS, and the odometer gives us that velocity. Overall outcome of that is a vehicle trajectory. What we normally get asked at this point is, if we're using GPS, what happens if that drops out where we have high buildings and trees, for example? What would normally happen is the IMU will calculate the path until the GPS then drops back in, and the absolute accuracy and the drift of that trajectory would depend on the exact IMU that was purchased. And so what if I'm working in a tunnel with no GPS? Well, in that example then, in that situation, what would happen is we'd be limited to the IMU accuracy unless we actually had a control network of targets to maintain the accuracy and to limit drift on the trajectory. In terms of the georeferencing of the data, okay, what we would normally do is use a base station or a smart base GPS data. And we also have the combination of that with the vehicle GPS data. So as a combination then, the per mission GNSS receivers are picking up accuracy of about 40 to 50 centimeters, However, using a static secondary triangulation from the smart base or the base station, we can increase that accuracy to 1 to 2 centimeters. And just to show you there's the vehicle. We have some, obviously the alignment between the two GNSS positions gives us a very accurate heading as well. Okay, helps to minimize dropout on the GPS. There are some options for the positioning as well. You can use a standard base station, like I said, or you can use a network base station. There are some disadvantages to either, or benefits and disadvantages to both. Obviously, you would need to have a subscription to a base network if you wanted to do that, such as the RyanX system, or you can just use a standard sort of GNSS receiver. Some positives and negatives either way, but both are obviously possible solutions. But using that base station, what we do is we pull that trajectory into or we sort of triangulate that trajectory. It gives a much better accurate position. So in terms of accuracy, you can see there the top line on the right hand side would be our accuracy with just the trajectory. So we're talking about up to, even we've slipped out to about 40 centimeters at one point there, but you can pull that back in again with that secondary triangulation using the smart base GPS to pull us down to 1 to 2 centimeters. So a little bit just quickly on the case study. I'll run through this quite quickly. This example that I'm just going to quickly show you is Rochdale to Brighouse and back. So we ran this as a case study just along the M62 in the UK. We set this up. We ran this through the night, an early morning session, and captured around about 60 gigabytes of data. You can see there we've got about 45 minutes either way. And anybody who knows this neck of the woods, we do have a sort of farm that's located right in the middle of the busiest motorway in England, so it's quite a recognisable area. Some of you may have seen the data video of this data we captured, but just to show you there, using about 45 to 50 miles an hour, we've got a 20 centimeter grid spacing on this data. One GNSS base station logging at 1 second intervals, and we have 360 images captured at about 5 meter intervals. So you can see the quality or the type of data that you can capture from a system such as this, which is obviously now in Autodesk Recap, and we could obviously then pass that on through the Autodesk solutions. A process so you can kind of see how this works, and I'll just run through this quite quickly. It's a little bit short of time here, but we effectively have one overall mission which we break down into separate smaller missions or smaller data sets, and all of this data comes out in the end in LAS format. So this may work now. Just to show you how the system looks as it's capturing the data, you can see we've got a computer sat on my knee here as we're driving along, and it's actually pulling out ladybug images from the ladybug camera onto the laptop, so we can see the data that we're capturing as we drive along, and we have all of the information about how well the system's linked and calibrated. So what we do for the data processing, then we have the laser and the photo information. We bring that together. We have the GPS and the IMU information. That goes into a software called a Planix POSPAC. And that trajectory that is generated from the GPS and the IMU is pushed back into the Statecode post-processing software, which combines with the laser and the photo information to then give us a sort of colorized point cloud with a trajectory. And we can export that. And like I say, normally that comes out then in LAS format to take into different software solutions. But here's just a quick run through the data processing. You can see obviously this is the trajectory that we generated from this case study, this trajectory along actually shown in Google Earth as a link through the software. But what we can then do is, because we have each of these different images, we can go back into the Statecode software and we can actually pick a particular chainage point, for example, and we can run the camera back and forward to show us the information or the data we've captured at that specific point. So if I then open up a spherical view, you can see just rolling my mouse button forwards and backwards, we can actually walk our way or drive our way virtually along this survey path. So here's this Stott Hill farm in the middle of the M62. You can see we have a full 360 panorama of the information just within the Statecode software here now. And if we did want to bring any of that laser data in now, what we would do is we could just load that in, And we can cut slices through that and sections through that to take basic measurements at specific points. Okay, so if I just load in a horizontal section or a cross section, you can probably see on the right hand side of the screen there's a specific cross section through that particular set of data, and we can roll that backwards and forwards, and we can take measurements within that there. In terms of coordinate systems then, and Peter will cover this in a little bit more detail, but we use OSNet in the UK, or OSGB, for most surveying activities. But because we need GPS to be logged at 1 second frequencies, we are recording all of the data on UTM coordinates. Okay, so there is a type of coordinate shift which Peter might cover in a little bit more detail later on. So the data is generally provided in UTM coordinates. Okay. Just to let you know before I pass on to Peter, it is possible if you want to combine obviously the Focus S static data with the mobile scan data. And here's an example we did in Autodesk Recap, just to show you that you can do that. So there's some data combined. Obviously, you've got to be aware of the accuracy differences between the two data sets, but within a certain degree of tolerance, you can get a good combination of the data.